So let's start with the last session today. I will present the next speaker is Luca Smaldone. He's from Charles University. He will talk about topologically inequivalent quantizations. Please, Luca, go ahead. I will tell you when.
Okay. Okay. Can you see
when
the
you
full
have 5
screen?
minutes left.
Yes.
Can you see all full screen? Okay, good.
Yes.
Yes.
Okay. Thank you for the introduction, Paul.
Please.
So,
Please, Luca.
thank you. I will present this work, recent work, collaboration with Giovanni Acquaviva and Alfredo Iorio. So, let's start directly. First of all, I will give motivation about why we started doing this kind of things. And because, as Alfredo already said this morning, and much more detail, we know that Bekenstein bound on entropy suggests that the Hilbert space of a quantum system in quantum gravity it should be locally finite dimensional. And this Hilbert space seems to describe some degrees of freedom which are more fundamental than matter and space-time and self. And so configuration of fields of some space-time should emerge at low energy. And we call this, following Feynman, this fundamental mode exons. Now, the problem that poses this kind of scenario is that exons must rearrange in different ways in order to form space-time and matter. And so they have to rearrange in a very rich variety of phases. No. And so there is a mathematical problem, first of all. This is clear because our world is full of different phases and so on. But from a mathematical point of view, we know that some von Neumann theorem affirms that all unitary reducible representation of finite dimension of Weil-Heisenberg group algebra are unitary equivalent. And so it's essentially there exists a unique quantization in a certain sense. And this is usually overcome in quantum field theory, which deals with a system with an infinite number of degrees of freedom. So in that case, Thom von Neumann theorem cannot be applied. And so we have inequivalent representations. And we have spontaneous symmetry breaking at different phases. In particular, it's common knowledge that spontaneous symmetry breaking occurs only at infinite for system in an infinite volume. And so, but there's another possibility. The Thom von Neumann theorem actually does not apply in quantum mechanics if configuration space is topologically non-trivial. A classical example is the one of quantization of a particle on a circle. And here in this work, we try to show that we deal with quantum field theory. We showed that this kind of topological inequivalence occurs in quantum field theory and can be treated as the standard, I would say, thermodynamical inequivalence. And we can give also a notion of spontaneous symmetry breaking at finite volume, which is more reasonable to us because we always see finite volume systems. So let us start. The system we are considering here, it's very simple, very known in a certain sense, which is a Goldstone type model, which is U1 invariant. And suppose we have spontaneous symmetry breaking of this U1 invariant, and we can write the Hug expansion of the scalar field phi, which is interacting field. Hug expansion is the mapping, which is weak mapping of the interacting field phi in the Fock space of asymptotic states or quasi-particle states, we'll say physical states in general, it depends. There are high energy or condensed matter and so on. And it is known that this is the form where f of the Hug expansion, where f is a generic functional and key is the Nambu-Goldstone boson, which controls the phases of the field phi. Now, very beautiful result, a very non-trivial result, is that the Heisenberg equation of motion for phi are invariant under the following boson transformation, where f is a function which follows the same equation as the Nambu-Goldstone field. And this is named as a boson transformation theorem. Okay, in case of f equal to a constant, this is just what is called dynamical rearrangement of symmetry. In the sense that if you translate by a constant the Nambu-Goldstone field key, you recover a phase transformation at the level of phi. So you see, you have a rearrangement between the level of interacting and asymptotic fields of the original symmetry. But it's more highly non-trivial for f, which depends on space and time. In particular, we are interested to the case in which f is singular in some point, particularly is non-Schwarzschild function. And then we can define in some point this field strand G mu nu dagger. And this situation is very interesting because it permits to describe formation of topological defects in a pure quantum field theoretical. This is quantum context. It's not semi-classic or something like that. No, this is a mechanism in quantum field theory. And so, in fact, we can define, for example, topological charge by looking at this field strand. And the case we will be interested in particular in the rest of the talk will be f equal theta. And this corresponds to the formation of the spontaneous symmetry breaking of linear vortex along the z-axis. In fact, we have, if you compute in this case topological charge, we have the usual topological charge quantization, where alpha must assume only integer values. So now we want to treat this boson transformation as it is a canonical transformation. We try to linear canonical transformation. We try to write it in terms of unitary operator G, which is not the same G as before. This is generator of the canonical transformation, which is defined here. And we want to study this at the level of creation and annihilation operator. In general, we cannot do in usual with usual Fourier transform because this is not Fourier transformable function in this point f. But a natural way of expanding here is in terms of a cylindrical harmonics here. I mean, Bessel function of integer order of first kind. And here we can define a set of creation and annihilation operators. And we can expand in an almost usual way our Nambu-Goldstone field. And then you can see that this creation and annihilation operator form a representation of the Weil-Heisenberg algebra. And we can write our transformation at level of creation and annihilation operator. This is just a translation of this type, where G is defined, it depends on F, in particular form of F. And last definition, I would say, we, as usual in theory of canonical transformation, we define the vacuum in the G representation as the state which is annihilated by annihilation operator. Now, it's known that necessary sufficient condition for the existence of the operator G, of fact that operator G is well-behaved unitary, or better said, is a proper unitary operator, is that the vacuum-to-vacuum transition amplitude here exists. For example, we take the case G equal to 0, G different from 0. And this physically means that if we stay on a vacuum, you have no zero probability, non-zero probability to go to the other vacuum. But however, if this vacuum-to-vacuum amplitude goes to 0, you have zero probability to go to the other vacuum. So you are stuck there, and you have unitarily an equivalent representation of Weil-Heisenberg algebra. And so in our case of this this translation, this is the form you can find by means of Baker-Campbell's formula. And just for simplicity now, I will show you the case of f equal 1. And which we need to take just fictitious mass m for Nambu-Goldstone field as a regularization, and limit n goes to 0 as to be taken after limit v goes to infinity. And you see that at finite volume, in this case, you have a unitary equivalent representation. So substantially all phases that you have here for different g are equivalent. But if you take the thermodynamical limit, you take finite volume limit in particular, you get inequivalent representations for different g. And this is almost standard, not done in this way typically, but okay. Now the interesting case, we take f equal theta, so the case of formation of vortex, of linear vortex, and this is the function g that you find. Calculation is non-trivial. You have to compute some non-convergent angle transform, so it's interesting also from technical point of view, but I don't want to enter into details. But the only thing, you can substitute this g inside this transformation, you see, and insert in the field expansion there, and you will recover.
You have 5 minutes.
Yes, perfect. So that's the result. And this is the result that we obtain in the case f equal theta. And it depends on 3 elements, essentially. 2 are related to the height of a cylinder, which has the axis along the z-axis, and lambda is the inverse radius of this cylinder. And so another parameter, epsilon here, or beta 2 epsilon, is the amplitude of a cut that we perform along a direction theta equal to 0, the angular amplitude of a cut. What does it mean? When we take h and lambda finite, or better, h finite lambda different from 0, we are in finite volume, okay? While if we take epsilon different from 0, it means we are trivializing the topology, because we are eliminating essentially the fact along the z-axis, and the figure that we obtain is homeomorphic to a sphere. And so the first homotopy group, the fundamental group here, is trivial, which is the important one for the stability of linear effects. But now we can do both operations. We can send or the volume to infinity, and so we obtain standard inequivalence, as shown also in the case f equal 1. Either we can send epsilon to 0. At finite volume, we can do it. And what we obtain that we have once more finite cylinder which is punctured, and this is homomorphic to a solid torus. So we have non-trivial first homotopy group, which is equal to z. And so you see, we obtain actually by limiting by a limit here exactly the same as the thermodynamical limits. In a sense, we are treating in exactly the same way, and we have unitary and equivalent representations of canonical commutation relations. So we want to review a little bit the idea of spontaneous symmetry breaking here, which are the characteristics. You know, it's invariance of the dynamics, non-invariance of the vacuum, and as a consequence, we should have disjoint realizations of the dynamics, which is guaranteed by inequivalence, equivalent representations, usually Nambu-Goldstone modes, which are in the spectrum, not in the spectrum, depends you have gauge or not. This is not an important point here. And typically, as I said, thermodynamic limit is assumed. But why? What's the meaning of last condition? We have just seen that we have disjoint realization, even finite volume. Typically, it is exactly because you don't want that a local operation can move you from one phase to another phase. So these are completely disjoint. Clearly, with local operation, you cannot change the boundary condition of fields on surfaces at infinity. But this is a sufficient condition, but not necessary condition. Clearly, this is also true in the case of topological inequivalence. So you have disjoint realization, and you cannot clearly change the global topology by means of local operation. So without last condition, we have spontaneous, we can say, I think reasonably, we have spontaneous symmetry breaking at finite volume. And we are putting on same level substantially standard thermodynamic, I would say, Landau-Ginzburg phases and topological phases. We are describing at the same level. So substantially, that's the message. We have an equivalent representation to Weil-Heisenberg algebra to non-trivial topology in quantum field theory. We have proved, and we are finding in a finite volume. So we put on same level topological and thermodynamical phases, and we have also a notion of spontaneous symmetry breaking at finite volume. I think it's practically very useful, and in particular, it would be very interesting to extend this consideration to non-trivial, more non-trivial transformation than the one that we have considered, like disclinations and dislocation with lead to Riemann tensor and non-trivial Riemann tensor to non-trivial torsion, like in the work crystal model by Kleinert and so on, and clearly applications to phase transition in exon model, where we're interested to these phases in finite dimensional Hilbert space. So more complicated, but we are going there. So thank you for the attention. Stop the sharing. I hope you managed to follow. Can you hear me?
I can hear you. I think the chairman, we can't hear the chairman.
Pablo? Yes. Well,
sorry.
Go ahead, Nick.
Yes.
Nick has a question. Go ahead.
Oh, sorry. Yeah, I couldn't hear what the chairman was saying. So thanks.
Okay.
Very, very nice talk, Luca, and very, very interesting ideas. I have two short questions. The first question is, how can I understand the absence of order parameter in two-dimensional systems, i.e. the Kosterlitz established phase transition in this approach? Can I, or?
No, this is essentially for four-dimensional. You mean you
cannot really, you cannot go down to 2 dimensions easily, you think?
Yeah, exactly. I don't think so. You mean breaking the two infrared number goals?
That's right. Yeah.
I don't think you can, in fact.
Okay, thank you. And one second question, quick question. Have you ever thought how, if you break spontaneously Lorentz symmetry, you know, there are people who claim that the photon is the Goldstone boson there. What's happening in your case?
I don't know. That would be very interesting.
Okay. Because that would be if you can topologically characterize that, if you find...
Actually, you know that in this case, it will be very interesting to look at, in fact, point defects that I think they are also mathematically treatable to the symmetry. Like, so I was thinking to work in this direction, sincerely, because you know, but I haven't done it yet.
Very good. Thank you very much. Thank you.
Thank you. Any more questions?
I have a small question. Yes, well, perhaps it has to do with two dimensions. But...
Yes, Marcelo has up there.
But if you want, proceed, Jorge, first, and I continue.
As you wish.
Go ahead, Marcelo.
Okay, I have a very short question. In these topological transitions, do you have critical exponents, as you find in normal phase transitions in field theory according to the normalization group, or how do you characterize the occurrence of such topological?
This is spontaneous symmetry breaking. You have a phase. I would say, you have non-zero vacuum expectation value or field. So it's which is space dependent. This is usual. So simply. It seems no one did calculation to check if there were an equivalent representation in this case. The problem with typical this is non-Fourier transformable, as I said. So you think I cannot define creation and annihilation operator or something like that. I think that was the problem in the past. But you see, in this particular problem, to the cylindrical symmetry of the problem, you can do by expanding in cylindrical harmonics, and you can. But this is spontaneous symmetry breaking with an ordered parameter.
Okay, thank you.
Can I ask the question now?
Yes, Jorge.
Yes, well, my question referred to two situations. One in 2D, which is the massive Schwinger model. There is known that Coleman showed that there were a topological invariant, which is a field, the electric field that do not go to zero, and so separate different phases there. And that he showed that is equivalent to have a certain length of the space. And the other thing I somehow remember is the case of anions, that is 2 + 1, where you put the flux there in the plane, which is perpendicular to the plane, and that create a situation that your configuration space is has a non-trivial topology, and so you have to put certain quantization corresponding to non-connected spaces, and that produce a topological phase and so on. Is it similar to what you are doing, or there is a difference?
I sincerely don't know. I don't know the examples you have done now, so I cannot compare actually.
Okay, thanks.
Perhaps I can comment a little, or
yeah.
I have time.
Yes, please.
Just briefly, the case Jorge is raising is among the family of standard topological phases. In something that you will find also in the quantum Hall effects and these sort of things. And that's exactly what we tried to do in this paper, like moving steps in that direction by using, let me say, the spontaneous symmetry breaking approach. So if there is one result of this paper that is noticeable, is that by using the same language, the same approach of QFT, the continuum approach, we were able to describe topologically distinct phases in the same language of phases distinct by spontaneous symmetry breaking. So perhaps in future we may even go into specific models where we may try to see those topological phases that we know that should be there, like in your case, or even older. There are plenty of these cases around, and see whether with our technique we will be able to describe those things in terms of a standard QFT as spontaneous symmetry breaking. I don't know if I answered a little bit.
Yes, thank you.
And about what Nick, and about what Nick said, it's in the last slide by Luca, when we have pointed to a singular translation vector there, which in the language of this crystal gravity, Hagen's Kleiner crystal gravity, yeah, that bit, you see that vector there is related to diffeomorphism transformation. And so if you can make that thing singular, okay, you are breaking space-time symmetry, and then geometric objects like the torsion and the curvature, which are geometric objects, and usually you just smooth them out over the manifold. They are coming from singularities in the topological sense. So it is of course just the words at this point, but the beauty of this work that Luca presented is it's a very specific example with very specific calculation. Of course, super simple, but we're going in that direction. Let me see.
You see, in fact, this is the same. I don't know if you can see. This is the same situation here. We just change symmetry. Eventually, you have a vector here. F is vector here, and as Alfredo was saying, or rank 2 tensor, and
exactly. We have to go up in the indices. So this is a scalar. We have to go to a vector, and then you can go rank 2 tensor.
That answers my question. Then you would have the photon as the Goldstone boson, for instance.
Could be.
After some conditions, of course,
could be.
I mean, it depends, because that's what I would expect to be a Goldstone boson in a spontaneously Lorentz symmetry. Not necessarily. It depends how the Lorentz symmetry breaks. For instance, in what Jorge is working on, the very special relativity, you don't have that. Or in mine, you don't have that because of external field. But it would be very interesting to see if you could.
Absolutely, absolutely.
Thank you.
What Alfredo said is that we are exactly using the same language. I tried to remark, it was very fast, but it's the same language as quantum field, spontaneous symmetry breaking. This is standard spontaneous symmetry breaking. It's just we did the calculations substantially.
I mean, if you take those textbooks like WAN textbooks, the gurus of topological phases, they make a strong point of the difference between topological phases and what they call Landau phases, Ginzburg-Landau phases, the spontaneous symmetry breaking. And with this motivation that's come from this fundamental theory, where everything should stem from one formalism. We've been trying to ask here how is this possible? I mean, is it possible we can unify these two concepts? And these are the first steps in this direction.
Exactly. They're exactly at the same level as you see.
Exactly. Yeah, this is the beautiful formula there. Yeah.
Okay.
That's the key formula.
You can discuss after the session. Thank you very much for the comments. Thank you very much, Luca, again.
Thank you.